Any other questions before I get started on stuff? So lab 3 people, today's the week 1 checkout. So if lab 3 people, when I put you in the breakout rooms, if you could just have open your model sim, your MATLAB plots, and the 3D butterfly plot that's associated with the week 1 checkout, just so that when either me or Bruce or Katie or some combination of us pops in the room to do the checkout, if you have all that stuff open, then we can just do it. And then you can, if you're not one of the first groups that we check out, you can continue on before the checkout. But just, if you could have that stuff open so that when we pop in, we can do the checkout and move on to the new stuff, and that would be good. Sound good? Okay. So I'm going to share my screen. My plan for today is to go over Pthreads, which is a Linux threading package, which will be useful for you you'll need it for lab 1 and lab 3, maybe lab 2, depending how you set stuff up. And then I'm going to introduce bus masters, and we'll see how far we get in that today. If that goes into the next time, that's fine. And I'm going to start with sort of a toy example. And then in the coming lectures, we'll go over a bus master for driving the VGA screen, if you wanted to drive the VGA screen with a bus master instead of from the HPS. And then one for driving the audio subsystem, which is of direct relevance then for lab 2. We'll see how far we get today. If that takes a few lectures, that's totally fine. So I'll share my screen and go to the course website as usual. And I'll start with the proto-thread stuff, Pthreads stuff. Pthreads on HPS. And I'm just gonna go to this example here. So I'm in the threaded keyboard insole console print counter example, opening up this software. And I'll copy and paste this into Sublime so we can do syntax highlighting. So some of you may already have experience with Pthreads, depending on, where am I going? View, depending on the projects that you've done. But for those of you that haven't, it is shockingly easy to use and works surprisingly well just kind of out of the box. It's one of those sort of rare things that seems to just work. Like nothing ever just works. This seems to just work. But what it allows you to do, like I said, is you can create and schedule threads that will be scheduled by the Linux scheduler. It gives you the ability to create mutexes to control access to global variables and other shared resources between threads. And then with a separate library, semaphore.h, that gives you access to semaphores for doing signaling between threads. So I just want to go over all that this example is doing is it is 3 threads. One of these threads is waiting for user input. A second thread prints out the user input and also prints out a variable that is counting as quickly as it can. There's a third thread that is just counting a variable as quickly as it can. So, and this is just, it's a very simple example just to show you how to put software like this together. And to show you how to lock out thread access to shared resources. So for example, the user input thread and the print thread, you need to control access to the UART lines so that you aren't trying to read in user input while you're printing stuff out. And then the print thread also needs to be careful about conflicts with the counting thread so that when it is printing the counting variable, the counting thread isn't also accessing that variable and producing nonsense. So we'll just walk through this. We do a few includes here. You include pthread.h, which gives you access to all the pthread stuff, semaphore.h. We create an input buffer where we'll store the user input. Create a couple of mutexes. So the word mutex, that's not a mysterious word to people, right? Okay, so a mutex is for it's a locking mechanism, whereas a semaphore is a signaling mechanism. So a semaphore allows you to signal between threads. A mutex will lock access to a particular resource until it is later unlocked by the same thread. So mutexes are locking within threads, semaphores signal between threads. Anyone know who came up with semaphores? Piece of trivia. I believe it was Dijkstra, of Dijkstra's algorithm. And the word semaphore comes from, semaphore is like flag signaling. You still see this in there's like naval flag signaling that these are semaphores. I believe that the analogy that Dijkstra had in mind when he was talking about these, he was thinking about, for trains, there's the flag that raises and lowers to allow a train to pass. So if the flag is up, a train will approach and stop at that flag until the flag lowers, and then it says go. So that notion of go to sleep until I tell you to wake up, that applies in that train situation. That's the analogy that he had in mind when he was thinking about this, as far as I understand. So that's where the word semaphore comes from, that sort of signaling. In any case, we create a couple of mutexes, one for locking the buffer that we're going to be using to store the user input, and one for locking the count. Create a couple of semaphores, one called enter condition, the other called print condition. The enter condition tells the thread that's responsible for gathering user input that the print thread is done, and then the print thread tells the print thread that the user input thread is done, and then a couple of variables. So then we drop into the actual thread definitions. You can see that each of these are void return functions that are while one loops that never exit. And this first example, this first thread, which is responsible for reading the keyboard, it waits on the print condition semaphore, so it waits for the print thread to be done. It locks the buffer that's used to store user input, asks for a string to be entered, stores that string in the input buffer, unlocks the buffer, and then signals via the enter condition semaphore to the right thread, and never exits while one. The right thread, it waits on the enter condition semaphore, locks the buffer, also locks the count variable, prints the user input value and prints the count, zeros the count, unlocks everything, and then signals back up to the read thread that it can ask for user input again. And then the final thread here is just counting as quickly as it can possibly count. So it is locking the count, incrementing it, and then unlocking the count. And I didn't put this example together, Bruce did. So you can see there are some notes here that if you were to not lock the count before incrementing it, this will count at 200 to 400 million times a second. Obviously, you don't want to do that, because if you don't lock the count as you're incrementing it, you're going to end up creating nonsense when this thread is attempting to zero the count while this thread is attempting to increment it. You'll end up zeroing a few bits or doing something unpredictable and bizarre. So you need to lock it, but in locking it, the overhead associated with these mutexes drops this speed to 9 to 10 million counts a second. Interestingly, Pthreads has a number of attributes which allows you to do a whole bunch of different things with these threads. One of those attributes allows you to force threads onto one core or another core. It'll also do this for you automatically, but an interesting experiment here that is worth mentioning is, suppose that we were to add another thread that is doing exactly what this thread is doing, just counting as quickly as it can. If we were to do that, the Linux will look at that and say, okay, we're pegging this particular processor at 100%, and it'll automatically migrate one of these counting threads to the other processor. As a consequence of that, these mutexes become interprocessor communication, an interprocessor communication scheme, which ends up slowing the whole thing down considerably. If you were to use a Pthreads attribute to force both of those counting threads onto the same core, then you recover your speed. Right, so you can play some games with this to try to get your whatever performance out of this that you might want.
Quick question.
Yeah.
So you said that it automatically gets like assigned to different cores, like the threads get automatically assigned to the different cores. So how do you force the threads to be on a certain core?
It is it's a pthread attribute that looks a lot like lines 106 to 110 here. I don't recall the specific set, the specific attribute that you set here, but you would do so using one of these pthread attribute setting statements. Bruce, do you want to elaborate on that? I think you're muted. I think you're still muted, Bruce, if you're talking.
Thank you. I was trying not to snark and snort while you were talking, but I forgot to unmute. There's the last example on that page is or in that section is a pthread set affinity, and you get to then, yeah, that one. In main, you can set the affinity to be either processor or,
yeah, right here. Okay, cool. Thank you. Does that answer your question, Nicole? Sorry, go ahead, Bruce.
There's a utility which is related to top, the Linux utility top. What's it called? It's a graphic version of top. And when you run that, you can watch the two processors pounding away trying to do this particular example as fast as possible. It's entertaining.
I think it's htop. Is that it?
You're right, htop.
Yeah, okay. Yeah, this answers my question. So you just basically do the set affinity, and then the I guess pointer that you're the address that you're pointing at the end of the last parameter CPU set, that's that's the CPU that you're constraining it to?
Yes.
Okay, got it.
And if you run both those CPUs wide open, you can feel the chip get hotter.
When you say wide open, what does that mean?
When both CPUs are running at 100%, just doing.
Oh yeah. Okay.
The FPGA becomes noticeably warm.
Okay, got it. Thank you.
So within main, nothing particularly mysterious is happening. We are creating thread identifiers, initializing our semaphores, being careful here to give one of them a value of 1 so that one of our semaphore locked threads can actually run at reset. Otherwise, nothing will happen. Everything will be locked out. We make our threads joinable through one of these pthreads attribute, which means if we set a join point in our code, which we do down here, the code will not execute beyond this line until all threads join, which is to say all threads exit. And because we've set up our threads such that they never exit, we will never get past this first join point. Then we create our threads. And then it just works. Any questions about this? Okay. So in that case, the next thing that I want to introduce is a bus master. And the bus master is getting to levels of complexity that it's not tremendously complex, but it's getting to levels of complexity that I don't feel I can reliably do like the real-time programming of this stuff. So I prepared an example yesterday that I'll walk through today instead of doing it in real time. But I thought I would start by just opening up the documentation for the bus master so that you can see where it lives and look through it if you care to. So down here in the links in the Avalon bus master peripheral page, there are a few examples here in increasing sort of levels of complexity. But down at the bottom is the documentation for the external to Avalon bus master. So, so what does this allow you to do? So what the bus master is like, sort of like the PIO port, it's a piece of IP that you can drag and drop onto the QSys bus. But unlike the PIO port, so the PIO port, it was a bus slave. So this is a bus master that allows you to, within your Verilog, manipulate the bus slaves that you have on your Avalon bus within Verilog. So you drag and drop this onto the bus, and it allows you to, when you export the conduit into your Verilog, it will export all of the signals shown here on the right side of this diagram, right? So when you export this in that computer system.v file that QSys generates, you will find 1, 2, 3, 4, 5, 6, 7 new wires appearing in that system that you can tie to your own Verilog to manipulate this bus master. And they all have pretty self-descriptive names. So one of these is address. So the bus master is going to write 2 specific addresses on the bus. It'll be writing to the particular addresses associated with slaves on that bus. So I'll show you this in a moment. But if you were to put, for example, if you were to put a PIO port on this Avalon bus at a particular address, you could point your bus master to that address and write to it. The same is true of the VGA, the same is true of the audio stuff. We'll go through all these examples. So one is the address that you're writing to. The next one is the actual data that you're writing. There are 2 1-bit wide signals that just indicate whether you want to read from the bus or write to the bus. There's byte enable, which is it does masking. So this allows you to say, I want to send 1 byte, 2 bytes, 3 bytes, etc. Importantly, the only thing coming back to your Verilog from the bus then is an acknowledge, which signals a successful bus write or the completion of a bus read. And then if you're reading data from the bus, you're also getting data back through a signal here. Okay, so these are the handles that your Verilog is grabbing in order to manipulate the bus. And this becomes clearer, I think, when you look at it in practice. Is there anything else I want to show here? So yeah, if you want to look through this, there's a description of all of these signals. And then there's a diagram here of how these transactions are working. So suppose that we wanted to write to a particular address on the bus. Then in order to do that, we would set the write address, we would deassert the read signal, assert the write signal, set byte enable to whatever we need to in order to send the size, the number of bytes that we're trying to communicate across the bus. we'd put the data into the right data line here, and then we wait. And we wait until the BusAC asserts, and then at that point we can step into whatever the next state in our state machine is, right? So we wait until this BusAC asserts, and then we know that the write is complete. Conversely, if we're trying to read from the bus, we set the read address that we want to read from. We assert the read line, deassert the write line, set byte enable to however many bytes we're trying to read back. And again, we wait. And when the BusAC asserts, that means our data is available on the read data line. It will not be available on the next cycle. So as soon as this BusAC asserts, we get our data from the read data line. Most of what you're going to be doing is writing to the bus. You may do some reading, but most of what you're going to be doing is writing. So let's take a look at an example. So this is something that I contrived yesterday based on the first couple examples on the web page associated with this EBAB. But I'm closing these because I want to first focus on writing to the bus, and then I want to focus entirely separately on reading from the bus. So we can take a look at this QSys layout. Some of this stuff looks extremely familiar. As usual, we have the system PLL on here. As usual, we have the ARM on here. And then below, the big sort of new thing that we're talking about here is we have this external master that we've put on the bus. This is available within the university program over here in bridges, external bus to Avalon bridge, right? So if you wanted to add this to the bus, this is where you would find it. And then when you do add it, if I were to double click this, there are only a few parameters that you actually set when you add this to the bus. The first is the range of addresses that you want to be able to address with this bus master. And the second is the width of the data that you want to communicate using this bus master. And then we hook it up. So how do we do this? As usual, we hook up the clock to the system PLL. We hook up the reset lines to the system reset and the HPS reset. And then because this is a bus master, right? The PIO ports are bus slaves. Because this is a bus master, this is creating a new lane over here on the left side in order to hook slaves to, right? So when you put a bus slave on, you're hooking it up to something over, some master over here. Because we're putting a master on here, it is creating a lane to which we can attach bus slaves. So this Avalon master is creating a lane over here that we can hook slaves up to. And then the external interface, we'll get to in a moment. This mostly lives in the Verilog, but we double click here to export this conduit into the Verilog, and that produces all those signals that we were just looking at in the data sheet that we'll drive using a state machine. But we'll get to that in just a second. So we have this Avalon master lane that we can hook things up to. So we'll put a slave on here that the master will drive. And in this case, we're putting on just a PIO port, which I have given the name LED display. In the Verilog, I'll show you that this is hooked directly to the LED output. So we hook this up to the clock, we hook up our resets. Note that this, ordinarily, in the previous examples when we were talking about PIO ports, we had them hooked up to either the lightweight bus or the AXI master, the lightweight master or the AXI master. This PIO port is not hooked at all to the ARM, right? So this is hooked up, the Avalon memory map slave input here of this PIO port is hooked up to the bus master and not to the ARM whatsoever. So this is totally separate from the ARM. We do have, and then we have a second PIO port here. So I should say that what I want for this program to do is On the HPS side, I want to be able to punch in a number and send it over a PIO port into the Verilog. And then I want for this external master to take that number that I communicated over the PIO port and do a bus write to the LEDs so that the LEDs show the number, the binary representation of the number that I just entered. So phenomenologically very similar to the examples that we saw for the PIO ports, where I punch in a number and the numbers appear on the LEDs. But instead of having the PIO ports mapped directly to the LEDs, it's going through this bus master. So I'm communicating the number that I want on the LEDs to the bus master. It's putting that number into its write data parameter and sending it to the address of the LEDs so that the LEDs then show the number that I want to write. We'll see this in Verilog, but that's the goal here. So the PIO port that we're using to communicate the data that we want the bus master to send to the LEDs, that's a PIO port as usual. This is exactly the setup that we've looked at in the past couple of lectures, where in this case we have this hooked up to the lightweight bus. So this does communicate with the ARM. The LEDs themselves do not communicate with the ARM. So then over here in the memory offset section here of QSYS, I'll point out a couple of things. The LED displays are at an offset of hex 20 on the EBAB bus. So when I fill in the address parameter for the bus master to communicate the data to this PIO port, the address that I will choose in order to communicate with the LEDs will be hex 20. That's where these LEDs live. And the bus master does not have any addresses over here because the bus master is generating addresses. The bus master is sending information to addresses. It is not consuming addresses. So it does not have any addresses over here. We'll go through this a few times.
Quick question.
Yeah.
So can you have multiple of these external buses? And if so, how many? And then additionally, you know how you said that you could read data back from, you can both read and write data. So then if you are reading data, does that mean that, I guess whatever is sending you data, it's just putting it on the bus lines, it's not actually sending it to memory? Is that why it's not consuming addresses even if it's reading? So yeah, there's two questions there.
So if it's reading data, you are directing it to a particular memory address. It's getting data from that address and then communicating it through the bus back to you.
Okay, got it.
So in the example that I haven't gotten to the bus read part yet because I didn't want to confuse things, but when we get to the bus read part of this, I'm going to point it to the switches, okay. And it's going to read the value of the switches and then communicate that information back to me through the bus.
Okay, that makes sense. But yeah, so the first question I had also was about having multiple external buses.
So yes, I believe you can. Bruce, can you confirm that? I've not done that.
Do you mean multiple bus masters?
Well, so yes, but it's one master per bus, right? So my question is can you have multiple buses that are this EBAB type?
Yes, as many as you want. And every one of them will produce a new lane on the left-hand side of the QSYS development screen. So, if you did 25 or 30 of them, you'd run out of room to see anything else on the monitor. But you could do that. Typically, you're going to generate one or two bus masters because you're going to be doing something because the Verilog code is going to accumulate the data into one stream, basically. Does that answer what you were asking?
Yeah, I mean, I understand now that I can have multiple of these buses, but like when you say that you can have as many as you want, like how is that qualified?
Well, when you run out of space on the screen to see what's going on, there's no natural limit on bus masters because each one of them has its own address range. I mean, sooner or later you'll run out of room on the FPGA. I would guess that if you wanted to, you could put dozens of bus masters out there, more than you'll ever do.
Okay.
Each one of them takes some FPGA hardware, and so if you did enough of them, you'd run out of FPGA ALMs, right?
What's an ALM? But yeah, I do understand that you would run out of hardware. I guess that's why I was I was trying to ask, like, do you like
ALM is advanced logic module.
Okay.
So that's kind of a lower level of detail than what has gotten to so far. It's down in the bowels of the FPGA, but it's what is the target for the Verilog that you write? It's an ALM mostly.
Okay, cool, thank you.
Any other questions about the QSys before we take a look at the Verilog? And this too, like almost everything in this class, it sort of is something that makes sense in aggregate. And when you look at the individual pieces, if we look at the QSys without looking at the Verilog, it's a little bit more confusing. So maybe looking at the Verilog will help clarify things as well. So let's do that. So I will start by going down to the computer system module that QSys generates to show you that in QSys, when we export this conduit from busmaster, it is producing these signals in the Verilog. Well, it's producing the signals over here on the left in the Verilog, and we are tying that to our own Verilog here, right? So these are signals that are defined farther up that we'll take a look at in a moment. But this is everything that the QSys is generating associated with this busmaster. And it's all the stuff that we saw in that data sheet, right? The address, byte enable, read, write signals, write data, acknowledge, and read data. The other thing I want to point out here is if we take a look at the two PIO ports, this is the PIO port that is on it's this PIO port here, the LED display that is hooked up directly to the busmaster. This is the one that we want to tie directly to the LEDs. So in order to do that in the Verilog, I have the exported QSys signal tied to the LEDR register, which you'll recall is the wires that go directly to the LEDs on the FPGA. So when I write to this, I am writing to the LEDs. Okay. And then we have our other PIO port, which is hooked up as usual to the ARM, as we've seen before as the ARM. And this is hooked to a wire that we'll see farther up that we created called LED from HPS. So this is the command that we're sending to the Avalon bus, or to the bus master to write to the LEDs.
Hunter, I have a quick question.
Yeah.
When we write to the LEDR, does it also modify the hexadecimal display at the same time?
It does not. It does not. The hexadecimal display has their own set of registers, which if we look up here, It's this set here. So if you write to hex 0, then you're writing to the first hex display. It's a 7-segment display, so there are 7 bits associated with this register. If you write to hex 1, it's the next one, and on and on and on. These are active low. So if you were to write 7 ones to hex 0, that means that output display is all dark. If you were to write 7 zeros, then all of the 7 segments are lit up, and you get an 8, basically.
It's kind of interesting because when I replicated the PIO lab that you did in terms of like inputting a number into the HPS and then having that show up as a decimal or a binary like LED, for me, it actually ended up modifying both the LED and the hexadecimal display. So in that Verilog, there is, and we can look at it together if you'd like, but there is an assign statement that is assigning one of the values on those PIO lines to the hex display. So there's an assign that's assigning the LEDs and then a separate one that's assigning the hex displays. If you were to comment out the hex assign, you would still be writing to the LEDs without writing to the hex. Got it. Okay, thank you.
Okay, so let's look at the actual interesting stuff here. So we have a few register and wire declarations. We have LED from HPS. This is the signal that we've wired to the PIO port coming from the ARM that we're going to be typing a number into. This we're not going to look at yet, that's for reading. And then we have an LED register that we're going to be using to hold the value that we want to put into the LEDs. And then we have all of this stuff here that we tied to the QSys generated Verilog down below. So we have a 16-bit wide bus address. We have a 4-bit wide byte enable, the bus read signal, the bus write signal, the 32-bit wide write data register, the 1-bit wide bus acknowledge, the 32-bit wide bus read, and then a variable that we're just using to control the state machine. So let's take a look at this state machine. And for the bus write, the only relevant states here are the first 2. So all that we're doing here is we're saying if the state is 0, and because I don't want this to just be running all the time, I'm saying if the state is 0, and if the value in the wire attached to the PIO line that goes to the ARM is different from the stored value, then execute this state. And what it'll do is set the state to 1. It will put the value that's on the PIO wire into this storage register, right? So that these two are the same. And then when it comes back up, if those two are the same, it won't run. So basically this only runs every time I put a new value in. It sets the bus write data to the value that we've sent in from the HPS over the PIO line. So it sets the bus write data to this LED from HPS, which is defined here and which you will recall we've tied to the PIO port that goes into the lightweight bus on the ARM. We want to send 2 bytes. We set the bus address to hex 20. Why is the bus address hex 20? It's because in the QSys, we put the LED display at hex 20. So this is where we want to write. If you were doing something, so in our case, because we're writing to the LEDs and only the LEDs, this is a constant. We're always writing to the same bus address. If you were doing something like writing to the VGA, remember in the C code for the VGA that we looked at last time or the time before that, we were looking at a base address and then offsets from that base, right? So if we were writing to a specific pixel on the VGA, this bus address would be different for each pixel. We'll look at that in a coming lecture. In our case, we're always writing to the same address. We're just writing to the LEDs. If you're writing to a VGA screen, then you would change the address that you're writing to for each pixel. And then we assert the bus write. So then we drop into state 1. We try to drop into state 1. We wait for the bus act to return. And then only once we've gotten the bus ACK, we leave this state and set the bus write to 0. If we were only doing bus writes, I would have set this back to 0. I have this dropping into the states then that do a bus read that I haven't gotten to yet. Okay. So we set the data that we want to write. We tell it how many bytes we want to write. We tell it the address that we want to write to. And we assert the write signal, and we deassert the read signal. And then we wait for the bus to say, okay, I did what you told me to do. And then we move on. And when we do this, it will write the value that we have put in write data to this memory address, which is the base address of that PIO port that we've tied directly to the LED hardware. What do you think? So let's just take a look.
I had one comment on that, and that is that the byte enable is 1 HOTS. So byte enable 1 means the 2 lower bytes. It does not mean 3 bytes. It means the 2 lower bytes.
Okay, thank you. So if we look at the FPGA, oh, you can see I was experimenting with. Turns out some masking tape over the hex displays does actually improve readability. Same's true with the LEDs. So if you're having trouble reading stuff, let me know and I'll put some tape over your hexes and over your LEDs, and it just dims them just enough to kind of be right for the camera. It's a pain in the ass to get the LED under there, or the tape under there, but that's okay. Maybe I'll take this off temporarily, put tape down. Anyway, so let's run, we'll look at the C code in a moment, but I just want to show you the behavior. So I am going to write some value to this PIO port. Let's write 0, and the expectation would be no LEDs will light up. Let's write, we have 10 LEDs, right? So in order to fill those up, let's write 2047. Fill up the LED, we can write in intermediate values. So the behavior looks very similar to the PIO example where we were sending data in over a PIO port. And in that case, we had tied that PIO port directly to the LEDs. It looks like that's still happening. Recall that what we're doing here is the data that we're punching in over this interface, 45, is being sent over a PIO port to the bus master. It's being put into the bus write data connection for that bus master, and then being communicated by the bus master to the address where the LEDs live. And then when it writes that data to the address where the LEDs live, the LEDs light up with whatever we've told them to light up with. Make some sense? And then, so we're not gonna have time to do it today, but next time we're gonna look at reading from the bus. In this case, I'm reading the value of the 10 switches. So if the 10 switches were a 10-bit binary number, I'm reading back the value of that in hex, which I'm reading as 03CE. I happen to know that's right. How do I know that? How would I know that's right without going into the lab and looking at the switches and figuring it out? Any thoughts? You could tie the switches directly to the LEDs, right? So you could put the value of the LEDs to be the same as the switch register and see which LEDs light up. And then even though you can't go in and throw the switches yourself because you can't get in, we can't touch the hardware, you can use the LEDs to check the state of the switches to do these sorts of sanity checks. So that's how you might do it. Set the LEDs to the value of the switches, see which ones light up. Then you know what the switches are set to, and you can do these sorts of tests where you see if you can then read from those switches and get the right number. We're gonna linger on this for a little while, okay? So next time we'll do a toy example of a bus read. We may revisit this example a little bit, and then I'm going to do some applications of this bus master. This is just sort of, there's no real good reason to use a bus master in the way that I'm using it here, other than to figure out how it works. But in the next lecture or 2 lecture or 3 lectures or so, we'll talk about using this to control VGAs and audio, and that is relevant.
Question.
Yeah.
So is the reason why we're using a bus because, so I'm just trying to like figure out what the advantages of using the bus are over just tying it directly. And is it because of like throughput, or just because you're gonna have to use a lot of IOs, and you have like a limited number of those? I'd just like to know why you would use the bus instead of just tying it directly.
Bruce, do you want to answer that?
Sure. So for this example, as Hunter said, it doesn't make much difference in performance. But if you were doing some big calculation on the FPGA, let's see, lab 3, which is Mandelbrot set, you don't want to send the data over the HPS and then have the HPS send it back to the VGA display, because that goes across the Avalon Axibus bridge twice. Rather, you want your code to be able to control other peripherals. To do that, for instance, the VGA, to control other peripherals, you must be a bus master. So by writing a bus master, it gives your code control over anything else on the FPGA, including, if you're slightly insane, the HPS main memory. You can write to Linux managed memory if you are brave. Does that answer it?
Yeah, so just like in this example, it's because the HPS is already controlling the outputs, but in the situation where, like you said, the FPGA needs to directly control peripherals, then you would use
Correct.
it. Okay,
correct. This is really, the kind of example is really good for exercising your understanding of the bus master, where you're trying to figure out what all this jargon means. But once you do that, then you're going to swap around and use the bus master to control this stuff. Let's say audio synthesis.
Okay, got it. Thank you.
It would be unusual to use a bus master to control the LEDs, right? So this is just for figuring out the mechanics of these things so that you can then tie it to other peripherals, like Bruce was saying. Okay. We'll keep talking about this stuff, but you can start playing with it if you'd like. If any of you are feeling particularly sporty, you could attempt to, you could write a bus master for the VGA display for lab 1, if you were so inclined. You don't have to do that. You can control it from the HPS for lab 1. You'll have to do that for lab 3. But if you're feeling ambitious and if you want to work ahead on some stuff that will be relevant for much later labs, then you can do that.
In lab 3, the baseline code is the HPS calculating a Mandelbrot set and sending it across the bus to the VGA. The next level up is to write a bus master that controls the VGA directly from your calculation code. The next step after that in speed is to throw away the VGA bus slave and write your own bus slave for the VGA. And then you don't have to, or you don't even have to put it on the bus. You can bypass the bus completely and do this all in parallel on FPGA fabric. It's a little bit convoluted.
Okay, I will see most of you in about 90 minutes. And the rest of you, I will see on Monday. Have a good weekend.